So now that we've got this formula for finding the surface area that we get from solid of revolution, we're going to look at some examples of how we can use this thing. So what I want to do first is I want to see if we can find the surface area of a spherical cap. And so what I'm doing is I've got this graph. It's a unit circle, right? And we're going to rotate that around the x-axis. And if we do that, we get a sphere. So what I mean by a spherical cap is if we come in here and we cut off a piece of the sphere. This section here on the outside is what we call a spherical cap. And that's what I want to find the surface area of. So to do that, we're going to use our formula here. And I'm going to take my equation and I'm going to solve it for y, right? So I have f of x. So this becomes y squared equals 1 minus x squared. So y is the square root of 1 minus x squared. And if we differentiate this, y prime is 1/2 1 minus x squared to the negative 1/2 times negative 2x. That's a chain rule. And we get some cancellation here, and our result is negative x over the square root of 1 minus x squared. Now, we want to go from 1/2 to 1. So to do this, we're going to have to integrate from 1/2 to 1. So there is that technicality. Our derivative is not defined at 1, so it's not continuous there. Now, that is a concern, right? But it turns out, remember, what the formula says is if the derivative is continuous, then the formula works. It really doesn't tell us anything at all about what happens if the derivative is not continuous. Maybe the formula works, maybe it doesn't in that case. And this is a situation where we actually are going to get a valid result. Right, so I'm going to go ahead and continue with this here. I'm going to do the integral from 1/2 to 1. I'm going to put the 2 pi on the outside. F of x is the square root of 1 minus x squared. And then we have, this is times the square root of 1 plus negative x over the square root of 1 minus x squared dx. Okay, so now we've got some algebra to do here, some simplifying of this thing. This is 2 pi integral 1/2 to 1 square root 1 minus x squared times the square root of, I'm going to do a common denominator here. Well, let's simplify the square first. 1 plus x squared square root, that's going to be positive now, 1 minus x squared, no square root anymore, dx. And then I'm going to need to do a common denominator here so I can add these things together and make it one fraction. 1 minus x squared over 1 minus x squared. So my next line will be 2 pi integral 1/2 to 1 square root of 1 minus x squared times the square root of, that's just going to be 1 in the numerator, so it's 1 over the square root of 1 minus x. I keep wanting to put that square root back in. Over just 1 minus x squared dx. And look, this is nice. Everything cancels. Right, the square root here cancels with the square root down here, and we're left with 2 pi integral 1/2 to 1 of dx. Oh, that's the easiest integral there is. So this is 2 pi x from 1/2 to 1. It's 2 pi times 1 minus 1/2, which 1 minus 1/2 is a half. So this is 2 pi times 1/2, which is just pi. Pi square units, right? So there's the surface area of my spherical cap. So what I want to do here is I'm going to take a parabola, y equals x squared, and I'm going to rotate it around the y-axis. And I'm going to do this from x equals 1 to x equals 2. So I'm going to get something like kind of a washer kind of thing here. All right, and I'm doing this around the y-axis. Remember, there's nothing, I've said this many times, talking about these integral applications. There's nothing magical about the x-axis versus the y-axis. To do this around the y-axis, I am literally just going to reverse the formula, and instead of doing f of x, I'm going to do g of y, and instead of f prime of x, I'm going to have g prime of y. It's going to be exactly the same process. So the first thing I do is I need to make this into a function of y, right? So if I solve this for x, this becomes x equals the square root of y. And you can see I only want the positive y values here because everything is up above the y. I only want the positive x values because we're doing this from x equals 0 to 2. And what's that going to give me for y values? Well, when x equals 0, y is 0. And when x equals 2, y is 4. So those will be my new limits of integration. So I'm going to integrate this thing from 0 to 4, 2 pi square root of y times the square root of, and now I need the derivative, right? X prime is 1/2 y to the negative 1/2. And I'm not concerned about the discontinuity because we're going from 2 to 4, and the function, that derivative is continuous on that range. So what do I get then? This is going, now I need to square it, and let's go ahead and do that here. X prime squared is going to be 1 over 4y. All right, so let's put that into the formula here, and let's see what happens. So then this becomes 1 plus 1 over 4y dy. So we're going to have integral 0 to 4, 2 pi, square root of y, square root of, I need a common denominator here. This will be 4y plus 1 over 4y dy. Now look, we're going to get some canceling going on here. Let me rewrite this again. 0 to 4, 2 pi, square root of y times square root of 4y plus 1 over 2 times the square root of y dy. So all sorts of things cancel, and this is just pi integral 0 to 4 square root of 4y plus 1 dy. Now I'm just going to do a u substitution. We'll let u equal 4y plus 1, du equals 4 dy. So dy is du over 4. And if we make that replacement here, this becomes pi integral 0 to 4 square root of u times du over 4, which is, let's bring that 4 out, pi over 4 times 2/3 u to the 3/2, 0 to 4, power rule there. And then I'm gonna go back to x's. So I'm gonna get a little cancellation there. This will be pi over 6 times, what was u? 4y plus 1 to the 3/2 from 0 to 4. And we'll put our numbers in there, pi over 6 times, if I put 4 in, that's 17 to the 3/2. And you see, this is nice. If I put 0, well, if I put 0 in there, it's going to be minus 1 to the 3/2, which is just 1. And that's it. Right, there's my answer. Right, there's the surface area of this rotated parabola.